due to time constraints, I really want to move on to our last speaker today. That is Dr. Ahmed. Ahmed is working on developing new techniques similarly to improve the fracture toughness of composite joints. He was able to show how one can improve the overall strength of a structure by selectively weakening it. These bio-inspired sacrificial crack techniques will be the topic of his presentation. Go ahead, Ahmed.
Thank you, Bram, for the kind introduction. I am Ahmed Wagih, a postdoc at KAUST. So this work, it's entitled Mimicking Biological Adhesion Systems with Improved Fracture Toughness by Embedding Sacrificial Cracks Inside Adhesive Joints. So yeah, the outline of my presentation today, it's introduction and objectives, and followed by experiments, toughening mechanisms in bio-inspired composites, and topology effect of this adhesive layer, and I will finish with conclusions. First, the introduction. So it's, as it's known, biology, it's full of inspiration for everything. So one of the systems that have a very good adhesion, it's Miletus californianus. So this Miletus californianus here, how this work, and see when it's stuck with the surface adhesive layer, so some kind of protein is injected by the placo, forming the adhesive layer here. So this is the adhesive layer, and this is the placo, which is this threads here. So it forms adhesive layer that's stuck with the surface. The white phase in this surface, it's the white phase, it's protein, which is adhesive in our case, and the black phase, it's voids. So additionally, the structure of the thread itself, so the thread, it's this part, the structure, it's full of voids, which gain this Miletus more toughness. This adhesive layer is tough enough to make the Miletus stacked over the rocks or other things in the sea, even with high-speed water and waves. So this is a good example of this is a good adhesion system here. So inspired by this biological adhesion system, we propose a novel adhesive joint that can tackle the three limitations. The first limitation is avoid complex surface treatment, provide progressive damage mode, and improve toughness. So the idea of this adhesive joint is to generate sacrificial cracks, which is marked in red here, inside the adhesive layer by inserting non-adhesive film inside the adhesive layer during bonding to act as the voids generated in the Miletus californianus, and also another example which I didn't show here, it's Gecko. So the objective of this work is to develop bio-inspired adhesive joint with improved fracture toughness and understand the different damage mechanisms during crack propagation. I will touch in just the manufacturing process and the test, because the bonding strategy, it's a bit different than the normal bonding strategy. So first we apply half of the adhesive on one of the adherent, then we place the PTFE film, which is marked in blue here. Then we put the second half of the adhesive, and then we cover with the second adherent. So the structure of the joint, it's something like this, with the gap between two successive cracks G and crack width P. The test matrix in this study, we study effect of P, which is the crack width, and G, the gap between two successive cracks and the adhesive thickness. We perform ENF test to characterize mode fracture toughness. And this work, 3-point bending test, and with loading 8.25 millimeter per minute. We used the carbon fiber reinforced polymer adherent material, and the adhesive was a commercial one, Araldite 420 with two different thickness. Timoshenko beam theory was used as data reduction method to compute the R curve and the fracture toughness. The toughening mechanism in this, I'll talk about the toughening mechanisms now. So here in this graph, we show the load displacement curve for the baseline joint and a toughened bio-inspired joint, which is L0502, which means a joint with 2 millimeter crack width and 5 millimeter gap. The response, it's quite different between both joints. For the black one, which is the baseline, once the crack initiates, it propagates very fast without any kind of without a high dissipation. So for the bio-inspired joint, the situation is different. So the crack initiates at point A here, and once the crack initiate, it propagates up to point B. At point B, another crack, a secondary crack, propagate at the sacrificial crack, which arrests the crack up to point C, and then the situation is repeated at each sacrificial crack, reaching at point G. Even at point G, which is a very large displacement, 25 millimeters, still unbroken ligaments can be seen here, which connect the upper and lower adherent. This results in a large toughness improvement, mode 2 toughness improvement, 52% in this case. For the topology effect, we study different B and G value for this bio-inspired adhesive joint. We reach to a conclusion that the lowest or the smallest crack length and the lowest G achieve a good improvement in fracture toughness and maximum load as well. The maximum load, yeah, it's different for it differ with the change of the P and G, but finally we get a conclusion that the maximum toughness improvement for this joint. So to conclude, we present here a novel bio-inspired adhesive joint. So we demonstrate improvement in mode 2 toughness, and in the presentation from Professor Gilles Lubinot yesterday, we demonstrate improvement in mode 1 toughness as well. So the improvement rate of the fracture toughness and maximum load is dependent on the sacrificial crack width and the gap between two successive cracks. The joint with small crack and small gap show larger toughness. The improvement rate is also dependent on the adhesive thickness. The thinner the adhesive layer is, the much effectiveness of our approach. Thank you. I would be glad to answer your questions if you have.
Thank you, Ahmed. I don't see. Oh, wait, there is a question in the Q&A.
Yep.
Zuhair Gassem asked whether this is related to crack blunting.
Crack blunting. I don't understand the meaning of crack blunting. What do you mean with crack blunting? So to explain, we can. Yep, probably we can discuss it in the chat.